What we're looking at covering is AS 1170 Part 2. It's our bread and butter. As a structural engineer, we need that standard to design buildings, and our building designs are very sensitive to a number of decisions that we make as part of our process of using that standard, in particular the internal pressures. So most of tonight will be spent looking about internal pressures. What are they? How do we make decisions about which internal pressures to use? And then we'll look at debris, because debris is a complication for internal pressures. We need to understand internal pressures and debris loadings. Okay, so design loads. Whenever we design any structure, we open up 1170 and we use a number of different parts. We are all engineers, and we're engineers that have an understanding of what the loads on our structures are going to be, and we need to use engineering judgment in order to make sense of those loading standards. Not only AS 1170 Part 2, but the others as well. And so if we think about the kind of decisions that we need to make, for example, we are designing a building sight unseen. We have no idea who's going to be using that building. We have no idea how they're going to be using that building. And yet when we're designing, we have to make lots of assumptions as to how they are going to use it, where they're going to put their loads in order to be able to design it responsibly. For example, floor loads. If we've got continuous beams, we have a number of different partial loading configurations we use to maximise either the mid-span moment or the over the support moment. So that's one way in which we make a decision at the design phase, so that whatever way the client is going to use that building, it will be safe and we'll have designed it responsibly. What about internal pressures? They're in the same boat. We don't know how the client is going to use the building, but the standard gives us a bit of help. And it says when we're determining our loads on the building, we're using net pressures that are a combination of internal pressures and external pressures. And in the note, it says generally the most severe combinations of internal and external pressures shall be used. If Mother Nature can think of a more adverse combination, this is what happens. If we don't think adverse enough, what happened here is a door blew in and a wall blew out. A door blew in and the roof blew out. Roof blew out here. So that if there is a more adverse loading condition and nature delivers it to our building, it will find out any weaknesses in our assumptions. Here's a building in the next shot that looks pretty good. But have a look at the purlins in that building. You can see that they've all started to buckle. From the outside, the building did look a little bit lumpy, but it's going to need a major amount of work to repair that particular building. So if we get it wrong, exciting and interesting things happen. Here, a door blew in. The door on the left of the picture here blew in. The door on the right of the picture responded by blowing out. So that if an opening develops that enables pressure inside the building is going to respond to that net pressure. All of those are in tropical cyclones. This next picture is in Perth. So here is a building in Perth that appears to have lost something. What happened? The garage door blew in. So a single gust of wind, it was a thunderstorm event, a big gust of wind blew the garage door in, pressure inside the building was able to lift the roof off. Okay, the garage was under the same roof as the rest of the building. So there an opening developed and problems developed soon after, again in Perth. And this is an industrial building. You can see that all of these garage or the large access doors have blown in. That pressurized the inside of the building, and this is the way the building responded. So that again you can see pressure in equals problems. Now when we're thinking about net pressures on buildings, so we've got net pressures on buildings, we start off with the external pressures. And external pressures are really well defined in the standard. There's not a lot of wriggle room in your external pressures. You look up your roof slopes, your dimensions of the building, and that will give you what the external pressures on the building are. And there are not a lot of surprises here. We get inward pressure, positive pressures on the windward wall. We get suctions develop across the roof and they're highest near the edges of the roof panels. We get negative pressures on the lee wall what pressures do we get on the sidewalls? They're negative again, so that we get negative pressures again on the sidewalls. So that's the external pressures, and not a lot of engineering judgment is required for them. But internal pressures are different. Internal pressures develop because of openings in the building envelope. Once we get an opening in the building envelope, it lets the outside pressures in, so that our outside pressures are coming into the building, and whatever pressure is on the surface that we have an opening in is going to now come into the building. So we've got different pressures on different surfaces. Wherever the opening develops, that is going to tell us what types of pressure can come into the building. And how much does the internal pressure change? It's a function of the relative areas of openings on different surfaces. So with some surfaces being pressure surfaces and other surfaces being suction surfaces, a lot depends on the ratio of the openings in those individual surfaces. Okay, and here's the way it looks. If we get an opening develop here on the windward wall, so here we've got an opening develop on the windward wall, we've got positive pressure on the windward wall, that's letting that positive pressure inside the building, and now it's pushing outwards on all of the surfaces. So that if we're thinking about net surfaces on the roof, we've got suctions on the upper surface, positive pressure on the undersurface, and we've got a vectorial addition that says we have now got a substantial increase in the pressure on the roof. That happens in an instant. So as soon as the opening happens, the pressure comes into the building. It's not a flow-through situation, so the building does respond instantly, and we get, in this case, almost a doubling of the net pressure on the structural system. So selecting the internal pressure, we're talking about deriving forces from the pressures. The pressures are a combination of internal and external pressures, and this is the most curious note that you will see in any Australian standard. Let's look carefully at the words in that note. Generally, it's a note, remember, and are notes mandatory or informative? Notes are informative, and it says, generally the most severe combinations of internal and external pressures shall be selected for design. Now, shall is normally associated with mandatory, but here it's in an informative note. And the reason why is it's pointing to another clause in the standard that is normative, and it says it here, combinations of openings shall be assumed to give internal pressures which together with the external pressures give the most adverse wind actions. So it's there in a mandatory clause, and that note is pointing to a mandatory clause and saying, look, you're not going to have any choice about how you select the openings. We have to choose the most adverse combination of openings. And then it goes to talk about what potential openings are. Are there any surprises in the list of potential openings? We've got doors, windows, vents, and then it says they may be open or they may have failed. So it's not a question of were they open, could they have become open by having broken. And holes in cladding caused by impacts of wind-borne debris during a major wind event. So that what we're looking at is some permanent openings. Those permanent openings are going to be leakage, so that the general leakage around a building, and the air conditioning engineers can tell us how leaky different types of buildings are going to be. Vents in the building. Sometimes we put external vents in the buildings. That is going to be a permanent opening. And then gaps in the building envelope. Sometimes they are accidental gaps, but sometimes they're designed gaps. So you may have something like a workshop that you're designing with a whole wall missing so that they can drive trucks in for maintenance. So that gaps in the building envelope, all of those are permanent openings, and then there are optional openings that could be shut or could be open. Now, here is where the engineering judgment comes in. We have no control over what's a permanent opening, but we do over an optional opening. So if something can be open, we can now then work out whether it's more adverse to have this particular potential opening open or shut. So that these are all optional openings. They could be windows, doors, large access doors. And if we're thinking about maximising the positive pressures inside, we're going to maximise openings on a windward wall and minimise openings elsewhere. And we can do that with our optional openings. So here are some pictures of permanent openings. Okay, we've got vents. So there's a large vent in an industrial building. There's a gable vent, a rooftop vent, so that there are those types of vents that are permanent openings. Then there are some optional ones. Now these are some optional openings that in every single case have developed because of the wind. So that this window wasn't left open, that was some debris that hit the window. Here's a garage door, and this is in the south of WA, and that garage door has been blown in by the wind. We've seen this picture before. That door has been blown out, and a whole bunch of windows are missing from that particular building there. So they're all optional openings that have been accidentally opened by the wind event itself. So in thinking about where an optional opening develops, that dictates what type of pressure we're going to get inside. Windward wall opening, we get positive pressure. Side wall opening, we get negative pressure. Leeward wall opening, negative pressure as well. Which one's going to give you the worst in negative pressure? Leeward wall or side wall? Now we're letting the external pressure or suction into the building. On the leeward wall, our CPE is 0.5, minus 0.5. What is it on the side wall? 0.65 at the front end, tapering down to 0.3 at the back end. So that the worst case for suction inside is going to be a side wall opening. But just also recognise that there are other things. So an opening in the eaves has the potential to pressurise the roof space. In general, if we're trying to maximise positive internal pressures, we'll look for openings on the windward wall. If we're wanting to maximise internal suctions or negative pressures, we'll look for openings on the side wall. So if we're looking at designing a roof or a suction surface, that's going to be most adverse. What surface has the most adverse loading for a negative internal pressure? Which building surface is going to have the most adverse loading if we have a negative internal pressure? The windward wall. So the windward wall externally is being pushed inwards. If it's sucked inwards by some internal negative pressure, then we get the biggest differential pressure across a windward wall. Okay? So, thinking about entrance doors, we're now going to look at a number of different elements of a building envelope and ask ourselves how they're going to perform. Now, entrance doors. There is an Australian standard for entrance doors, 2688. It's mandated by the National Construction Code, but there is no wind rating for entrance doors. There are no testing required for the door or its furniture. What happened in this door here is that the latches failed. So that the door latches failed, the door was blown in, and we now have a substantial opening in our building envelope. So doors can be left open. They can be blown open by a latch failure. They can be blown in or out by the wind pressure, or they could be broken by wind-borne debris. So these doors here have all failed under wind loadings. In each and every case, it's by some furniture failing. So either a hinge or a latch. And they are all recent photos from Cyclone Debbie in North Queensland earlier this year. Windows. Windows do have an Australian standard. That Australian standard is mandated, and it does contain wind rating. So that windows have to be wind rated, and window systems have to be tested in order to be able to publish that they resist that wind rating. They can be left open. They can be broken by wind-borne debris, and would you believe that in spite of the fact that they could be, or that they are wind rated, they could be blown open by either a latch failure or the window failure itself. How could that possibly happen? This was a non-complying window. All right, so it was a non-complying window installed in the building, and that window blew in. It wasn't able to cope with the loads that were put on it, and the loads were barely the serviceability load for that window, and the window failed. So because of a non-compliant window, we now have internal pressure in our building. Okay? Something simple, and it's becoming, unfortunately, quite reasonably common, could cause substantial internal pressures developing in the building. Here is a hinge that has failed under wind actions. Here is some debris, so that windows have the potential to cause problems with internal pressure. Can you notice what's missing in that picture? The big front windows that looked out over the Coral Sea are all missing. But along with it has gone the roof. And lots of things in the roof failed. There was the roofing failure of the roofing fasteners themselves, but also the whole roof tie-down system had failed. That building had clearly been designed for low internal pressures. So that if we get large internal pressures develop, then the rest of the structure isn't able to cope with it. So we've looked at doors, we've looked at windows, now large access or garage doors. AS/NZS 4505 is mandated in the National Construction Code only for wind region C and D. And if you are building in wind region C and D, you must use a wind-rated door to AS/NZS 4505. And it does require that that wind rating be verified by testing of the complete system. That's the door, the tracks, all of the furniture, the latches, everything. So that we can say, okay, well, in region C and D, a large access door is going to be wind rated. It should be able to resist the wind loads. What about region A and B? Okay, you don't have to comply with AS/NZS 4505. As long as it plugs up the hole, it is okay, right? Is it going to resist the wind? What do you think? What are your thoughts? Now, bearing in mind the cheapest door is going to get the job, it may not hold back the wind. So in wind regions A and B, this is what tends to happen with large access doors at less than the design load. Every picture I'm showing you today is of an event that is less than the design wind load on that building. So that we're talking about areas where things have gone seriously awry. Now, before it was mandated, before AS/NZS 4505 was mandated, we got non-wind rated roller doors even in the cyclone region. And that's what tended to happen. So you can see the roller doors are missing. No surprise, they were not wind rated. What else is missing? The whole roof. So that we've lost the garage doors, we've now got a big hole on the windward side of the building, we've now got serious internal pressures, and the whole roof structure has gone and an end wall along with it. That's the same building on the left there in that photo. This one here was a large hangar building, and the latch failed on that door and it got flapping, and the door destroyed itself and created a huge opening in the side of the building, one complete wall missing, substantial internal pressures in that building as well. So as a designer, recognising that we have to choose the most adverse condition, adverse combination of internal and external pressures, for each surface we have a process. We identify the most negative external pressure on that surface, and then we consider optional openings for that same wind direction that are going to lead to the most positive internal pressure. And then we would consider, all right, for the same surface, what's the most positive external pressure, and then consider the configuration of optional openings for the same wind direction that is going to lead to the most negative internal pressure, and we calculate the vectorial addition of those two pressures. So that we've got both permanent openings, which we're stuck with for both considerations. However, we do have the potential to look at different combinations of optional openings and change our internal pressures that way. So design wind events now. If we're thinking wind region C and D, the design wind event for wind region C and D is a tropical cyclone. You think about it, you get warnings of a tropical cyclone. Tropical cyclones can't sneak up on you, they're too big. So that we're looking at them on the radar, we're bombarded with them on the news, we know they're coming. We've got plenty of opportunity to make preparations for a tropical cyclone. That means we've got time to secure the property, protect potential openings, find screens and put those screens out onto the buildings so that there is time to prepare the building. However, a tropical cyclone is a long duration. Any idea how long tropical cyclones are going to bombard a site for? What do I think? What do you think? 24 hours. Yeah, well, that's a really bad luck tropical cyclone. The people of the Whitsundays thought they got a raw deal because they had it for 12 hours earlier this year. But 12 hours of really strong wind means that debris is going to be picked up time and again and blown around in the airstream. So that debris does happen. Regions A and B are a bit different. Our design wind events tend to be thunderstorms. So that we have a thunderstorm and a wind front will go through and we get a number of gusts and it's all over inside a minute or two. Okay, so it's a shorter duration event. But there's not a lot of warning. So that there's no important telecast saying, okay, 4 days' time this is expected to hit. It's a question of the sky suddenly goes bluey green and then suddenly the wind happens. Okay, so that people can be caught unawares without time to close openings. If you're operating a large warehouse and a truck pulls away from the roller door's still up and the thunderstorm happens, then you've got an opening. Okay? So there's not a lot of time to prepare. The duration is shorter and there tends to be less wind-borne debris. So how do we design in wind regions A and B? This is what the standard says. So in terms of wind regions A and B, the full area of doors, including large access doors and windows that are normally closed, shall be considered to be openings unless they have demonstrated that they are capable of resisting the applied wind pressure. Okay, so that's what the standard says we must do. So that our list of optional openings must include anything that is not wind rated and tested. And in wind regions A and B, that is lots of stuff, but primarily any entrance door. So any entrance door is not wind rated. You can't guarantee that an entrance door is going to be able to withstand the wind pressures. Large access doors, unless they're specified to comply with that, they're not going to be able to resist the design wind pressures. And then we may also think of things that could be left open. Windows could be left open. Large access doors that do comply with AS/NZS 4505 could be left open. And so that's our openings. We've thought of the way the openings are going to be configured on the building. Now our internal pressures. Now those of you with photographic memories may remember that there are two different tables for internal pressures in the AS 1170 Part 2. Those of us without photographic memory, don't panic because they're on the next two slides. The first one is table 5.1a and it looks like this. And table 5.1a has been amended a little in the Fourth Amendment, and one of the amendments is the title. It makes it clear where that is to be used. It's only to be used if your building has an impermeable roof and if the openings in the building are less than 0.5% of the wall area. Okay, so that we're not talking about things with large openings, we're talking about gently leaky buildings. Okay, and it also now defines what is permeable and what is impermeable. If it is less than 0.1% of the open area, of the wall area is less than 0.1% open, it's classified as impermeable. If it's between 0.1 and 0.5% open area, then it's permeable, and if it's more than 0.5%, you don't belong in this table. Okay? So that if an entrance door is open, then that's a lot more than 0.5% and you're not in this table. So even an open entrance door means we can't use this table. Okay, and all of the classifications are given in the notes under the table. The second table is this one here, where we're looking at the building having an opening area of bigger than 0.5% of the wall area. So if the opening area is bigger than 0.5%, you go into this table. And in this table, in the left-hand column, you can see as you go down, the opening is offering a bigger effect on the building. If we're looking at an opening area ratio of 6, what we're saying is that the opening that we're considering is 6 times as big as all of the other openings in the building. Okay? So it's the ratio of the area of the opening you're considering against all of the openings in all of the other surfaces in the building. So that if we've got a personnel access door open, that's likely to give us an open area ratio of something around 1, maybe 2 for smaller buildings. If we've got large access doors that are open, then we're up around 3 to 6. We're in the bottom part of that table. Now notice when we look at this table that as you go down, we get closer to CPE. CPE is the external pressure coefficient on the outside of the building where the opening is. So that if our opening is in a leeward wall, we're in the centre column in that table, and you'll see that we've got a couple of different variations, and then rapidly it jumps to the full external pressure on the leeward wall as the internal pressure in the building. And the same on the side wall, and the same if the opening is in the roof. Those are all suction surfaces. And with most of the building in suction, it's saying that it doesn't take much of an opening to suddenly generate a lot of internal suction. Okay? For the windward wall openings, the progression is a little more gentle. Okay, let's look at an example, and we've seen these pictures before. We've got an office warehouse in Perth, and you can see that it's got some vents. See above the canopy, there are some vents there, so that there are some vents in that building. The vents are only on one side of the building. As luck would have it, this was the windward side of the building, so that even before we consider the problems with the large access doors, we've got some internal pressurisation due to that vent. We've got leakage in the warehouse, and warehouses tend to be quite leaky. Then we've got optional openings. The optional openings include the personnel doors. It includes the large access doors as well. And then there are fixed windows and operable windows that are potential openings there down the other end of the building where the office part of the building is. If we look at now, with the large doors in the windward wall as open, our open area ratio for that building is 8.2. Thinking back to the table 5.1b, that's the very bottom row, and our internal pressure is going to be 1 times CPE for the windward wall, which is 1 times 0.7. Our net pressure across the side wall then is the side wall pressure, which is the minus 0.65, and the windward wall pressure, which is now our internal pressure of 0.7, giving us 1.29. Now, commonly, people would design a building like that for 0 internal pressure. If you were to design a building like that for 0 internal pressure, then your net CP across the side wall is minus 0.65. It is half what the wind is going to deliver if those doors are open. What factors of safety would we normally expect? Significantly less than that, so this is sentenced to fail, which is exactly what happened when the wind did blow those doors in. So the large access doors failed, higher internal pressure than the cladding or the structure is designed for, and we had substantial cladding failures and some structural failures as well in that building. Okay, how does that fit with robustness? What is robustness? Robustness is something that is captured in the National Construction Code that says a structure should be designed to sustain local damage with the structural system as a whole remaining stable and not being damaged to an extent disproportional to the original local damage. What was the local damage here? Some doors blew in. $40,000 would fix it. Okay? And what was the building's response? Was it proportionate? No, it wasn't. So that this is a violation of the principle of robustness. So that when we're thinking about our internal pressures, the amendment to the standard gives us less wriggle room in terms of making assessments of internal pressures, but it is totally compatible with the concept of robustness. Now we're going to look at wind regions C and D, and a lot of work in Perth is done for designing for these wind regions. And it says that doors, including large access doors and windows that are normally closed, and cladding elements shall be considered to be openings with an area equal to the greater of the full area of the element where it hasn't got a wind rating. Okay, so full area of any element that hasn't got a wind rating, or the area of opening that's going to result from debris impact. So that if debris hits something, what area of opening is it going to create? If you've got an unprotected window and debris hits that window, what is it going to create? An opening the size of the window, right? If it's going to hit some cladding, some steel cladding, what area do you think the debris is going to create? Often it'll punch a hole through the size of the bit of debris. Okay, and we'll see some pictures of that in a little while. So that they're the openings that we are considering. So our list of optional openings must include anything that's not wind rated and tested, and that includes entrance doors. Our large access doors are wind rated, but it may include items that could be damaged by debris as well unless they're protected. So for wind regions C and D, what internal pressures do we use? Now we've got our openings, and this is a change with Amendment 4 as well. Because what it says is that it doesn't give us the option to use Table 5.1a. Our internal pressures must only be taken from Table 5.1b. Because even in a reasonably gentle tropical cyclone, holes are going to develop more than 0.5% of the wall area. So that we're only looking at Table 5.1b, and in fact, it says that the opening area ratio shall not be taken as less than 2 unless we've got a particularly leaky building or everything in the building has been sealed up, in which case you can then calculate what it really is. So that this red box is where we have to be by default in wind region C and D. And so you can see that for all of our negative internal pressures, it's just minus the full CPE on all of our negative walls, okay? And for our windward wall pressures, it's going to range from 0.7 times the windward wall CPE, which is 0.7, so roughly a half, up to the full CPE value, which is plus 0.7. So we've got a range of positive internal pressures of 0.5 to 0.7, and our negative internal pressures are just going to be the external pressure coefficient on the building. And we'll look at an example of that too. So we're going to do an extension to a shopping centre in the Pilbara. So this is an existing shopping centre. It's got vents in the building. It's got leakage. Our optional openings are the entrance doors, and it's going to have some large access doors. These are existing large access doors. So this large access door, the existing large access door, hasn't been rated to AS NZS 4505 and is a potential opening. What about the entrance doors? They do become openings. And again, there's not a requirement in the NCC for them to have a wind rating. So if we now look at this building, just with the glass entrance doors in the windward wall, we've got an opening area ratio of 2.3. We can now design by interpolation. Our internal pressure is going to be plus 0.53. Combination of the internal pressure and the external pressure on the roof gives us a roof uplift net pressure coefficient of minus 1.36. A common design assumption is that the internal pressure is plus 0.2. If that's the case, that's what we get as our net pressure across the roof. The difference is 1.3. So that, in other words, if we've used 0.2 as our internal pressure and the entrance doors break, we have the potential to increase our net pressure across the roof by a factor of 1.3. Again, that is not going to be pretty. When we look down on a shopping centre, we see there's a huge amount of roof. So that's what we see when we look down on a shopping centre. Vast area of roof, all now overloaded by a factor of 1.3. What's the result going to be? Potentially not pretty. Now, what's concerned me is that a number of recent tropical cyclones has seen all of the cyclone shelters fill up and people shelter in large buildings, like shopping centres. So they will shelter in shopping centres. They did in Rockhampton in Cyclone Marcia. They did in Cairns in Cyclone Yasi. They did in Bowen in Cyclone Debbie this year. So that there are people in these buildings and the roofs are at risk. Now, one of the reasons that we have to think about tightening these restrictions on your freedoms for internal pressure is because these are often designed in a competitive environment. So if someone uses a low internal pressure, they've got low net pressures across their roof, they're going to win the job. Okay? So that the problem is that if we leave too much room for engineering judgment, people are making decisions that are going to win them a job, but then endanger the community down the track and lead to problems with robustness in the building. Another thing that has changed recently, and it's been strengthened in Appendix 4, is pressures on internal walls. So you've got internal walls inside a building, and not all internal walls are equal. If we're designing an apartment, we've got firewalls between the apartments that have to be totally sealed so that fire can't break through them. Those totally sealed walls are going to have a pressure across them if an opening develops in one of the apartments. And so we have to design those walls for those pressures. And there are other walls in the building. If we've got other firewalls in the building, but they're not between a space that's a potential external space, they're between internal spaces, they're designed for a net pressure coefficient of plus 0.4. And if we've got walls that don't have an effective seal, they should be designed for a net pressure of 0.3. So that's spelled out a little better in the standard. And it is real. Here's a photo that I've taken after a tropical cyclone, and you can see that wall has moved due to net pressure across an internal wall. Now that brings us to the last part of this presentation, which is about wind-borne debris. If we have really strong winds, those really strong winds are going to pick up stuff. It could be natural vegetation, it could be boats, it could be parts of buildings. But this is what tends to happen. This whole thing in the left-hand picture is a roof of a building that has travelled through the air for 500 metres, clearing power lines and trees before being arrested by the back of that house. So that was a bit of wind-borne debris, a whole roof, right? And you can see that it's done quite a lot of damage to the house, and it now looks as though the crumple zone on the roof has worked a treat. Okay, this is a photograph in Perth. So that in the background you can see a picture of a house that has lost its roof. Here is a piece of debris from that roof that has become embedded in the ground, not in Port Hedland, but in Perth. Debris really does happen here in Wind Region A. And so this piece of debris looks pretty close to the standard piece of debris that's given as the impact load in AS 1170 Part 2. Now, AS 1170 Part 2 is a loading standard. So it tells us what the debris load we could expect is. This is a representative debris item. And we're talking about 4 kilogram mass flying through the air at 0.4 times the regional wind velocity. It also gives a secondary one, a spherical steel ball, which is very, very small. And that one is only really used, and it's now spelled out in a note in the standard, if you've got a glazed surface behind an open screen, the glazed surface has to be able to resist that because it would get through the screen. So the change here is that in the past it said that the debris impact shall be equivalent to, now it just says shall be. So that you've got to do that mass at that velocity in order for us to say yes, with the energy is right and the momentum is right. Okay, and debris does happen. Here are a few shots of debris. That's what it does to buildings. And occasionally things catch bits of debris. Here are some trees that have caught pieces of debris, and you can see pieces of debris have punched all of the way through the tree. It is scary, isn't it? Would you want to be out walking, enjoying the fresh air, with that stuff flying around, seeing what it does to a tree? Okay? So that you think of the velocity that's been required to punch these through the tree. And let me tell you that it didn't hit pointy end first, it hit blunt end first and went blah, and the back end dropped off. Okay? So that was some debris that punched right the way through a palm tree, and it was fairly high up. This is a detail, that's where it sits on the building, and that is the roof of a two-storey house. Okay? So reasonably substantially high. Here's something else that's caught some debris. That is a building has caught that piece of debris that came in through the roof. And I said I'd show you a couple of pieces of debris that had punched their way through some sheet cladding. That's the kind of hole that they leave on their way through. So these are straight out of tropical cyclone events. Why do we consider debris loads? It's always been an option to consider debris loads. But it's possible to design any building without using debris resistance. There are two reasons why you might want debris resistance. One, we want to protect people from that stuff flying around. This is a cyclone shelter, and across the windows of the cyclone shelter is web-forged decking. Okay? So that is heavy enough to stop really big lumps of debris at high velocity coming into those buildings. There's also the option of some concessions on internal pressure, but seriously, it's not a big, it doesn't deliver very much. So that the CPI doesn't change too much. You still have to use table 5.1b, but you could, if you protect everything from debris, use a ratio of less than 2. So wind-borne debris. How do we work out whether or not a structural element can cope with it? With debris tests. Now the loading standard is a loading standard, it's not a test standard. And people have said, why isn't there a test standard? The industry is getting together and putting together a test standard. We're hoping it will be out in the next couple of years. But the idea is that debris tests are going to be completely repeatable, so that we're pinning everything right down. The detail on the debris item, the density of the debris item, even the radius of the curves on the end of the debris item, the rigidity of the support, where we strike it. And it all does make a difference to the way elements are going to perform. And debris is pretty powerful. Now, the debris velocity increased in 2011. Prior to 2011, the debris velocity was 15 metres a second. Why? After Cyclone Tracy, a lot of people looked at the damage and said debris is doing a lot of this damage. We have snowballs of debris taking out buildings. And they said, what is the speed this debris is moving at? And obviously they couldn't wind back the clock and pull out a radar and clock the debris doing the speed it was doing when it hit the building. So instead, CSIRO made up a cannon that would shoot the debris at different building elements, and they said, aha, if we shoot it at more than 15 metres a second, we produce the type of damage that we saw in Tropical Cyclone Tracy. So that 15 metres a second was in the standard from just after Cyclone Tracy right through to 2011. Since then, people have been able to look at, okay, what does the wind actually do in picking up debris? What speed does it accelerate it up to? So we get test facilities like this. An insane test facility. They have to ring the power station and say, can we start our fans now? Okay, so that a lot of energy is put into the airstream and they can work out what acceleration they get out of a piece of debris. And that is the reason that the standard has changed in 2011 and it's still there at 0.4 times the velocity of the regional wind speed. Okay, so in summary, we've looked at internal pressures. There's been a recent amendment to AS 1170 Part 2, and we've looked at what that means for us as designers in designing buildings to resist those internal pressures. The amendment clarifies the intent of decisions about internal pressures and restricts the options for internal pressures in cyclone areas. So in wind regions A and B, we can use either table 5.1a or 5.1b, and in the Fourth Amendment it makes it much clearer as to what the demarcation between those two tables is. And then in wind region C and D, we can only use table 5.1b, and the default ratio is 2 and above. Debris does cause unintended openings, and the standard gives us loads for debris. And it is important that we keep abreast of these things that are happening. The only reason that the standard is continuing to change is because when we look at buildings, even brand new buildings after tropical cyclones, we see there are problems. Okay, so that the industry still isn't quite right. We're asking ourselves, why isn't it working properly? Internal pressures is a major part of why some buildings don't work so well. Okay, just to close off, some of you may be wondering what the Australasian Wind Engineering Society is. It was a non-profit technical society set up in 1985. It serves to promote and advance wind engineering and industrial aerodynamics in the Australian and New Zealand and New Guinea regions. Primary activities, workshops, educational lectures such as this one, public seminars, quarterly publication of a newsletter, and some guidelines. So that this is the Wind Loading Handbook for Australia and New Zealand as a companion document for ASNZS 1170 Part 2. It's continually updated. It is available off their website. Membership costs you $100 for 2 years, and they do a couple of different things, one of which is the Wind Engineering Workshop and Wind Loading Day, which is coming up in April next year. There were flyers at the front. If you're interested in that, please get a hold of those flyers. And if you're interested in becoming a member of the Australasian Wind Engineering Society, their web address is on those flyers as well. Thank you very much. Thank you. Okay, yeah, the question was about how the Amendment 4 to 1170 Part 2 affects AS 4055, and effectively no change. That the internal pressures assumed in 4055 are entirely compatible with this amendment. And basically, it's always been the intention that that's the way internal pressures are interpreted, and there were notes that were in 1170 pointing people in that direction, but they weren't going. So it's now got to be a little bit more heavy-handed and say, right, here are your options, and they are closed down. But 4055 is compatible with those options. Thank you. So the question was, in wind regions C and D, if you've got a really well-sealed building with everything protected, the standard does allow you to have a different internal pressure coefficient, but you're still deriving that out of table 5.1b. So you'll be right up the top of that table with your plus 0 minus 0.3. It's essentially the same as you would have got from table 5.1a anyway, but you have to demonstrate that you do have that very low opening area. Okay, so that's the way that is handled. The question was about the 8mm ball. Do you have to test every single project yourself, or is there some certificates around? There are a number of glazing manufacturers who have certified that their product is able to withstand the impact of that ball, so that they can be used behind an open screen. So that there are products around that can resist that ball bearing impact and are therefore able to be used behind open screens. Generally, it's a laminated glazing product. So it's a laminated product with a reasonably thick plastic central layer. For wall claddings themselves and things like steel sheeting, the energy in the ball is not enough to trouble those. And the notes in the standard now say that that ball bearing test is really only appropriate for brittle surfaces that are behind open screens. Okay. So for anything else, the limiting one is going to be the timber debris item.